Okay, I hope you took some time to watch the Franz Klammer video. I wanted to watch it again, so I kind of took a little break there and watched it for a minute. And then when you go to this knuckleball race, the next thing is showing drag again and how drag works uh, uh, on on objects. And go ahead, for some of you that are baseball fans, go ahead and look at the knuckleball research. This is from the University of Illinois site. There's a guy, Nathan, Alan Nathan is his name. He's got like Dr. Nathan at the University of Illinois. He's actually a particle physicist, but he is fascinated by baseball. He loves baseball and all the physics around it and all that. So there's some things on, uh, what was his name? R.A. Dickey, the knuckleballer. And what's strange about when you watch is very wind up, and it looks like he's just playing casual catch with his son or something in the backyard. By the way, the knuckleballer actually throws the knuckleball, but it moves all over. It's really hard to hit. It's also very hard to throw strikes. And so I watched a playoff game when the Red Sox were in a play when were in the playoffs, and I can't remember who the opponent was. It might have been a World Series game when the Red Sox were in the World Series, the one they lost. And they brought out Tim Wakefield to pitch in a kind of a pivotal game and of the series. And the other team, they're like, okay, he's going to be throwing that knuckleball stuff that using the coefficients of drag and they're not analyzing it that way, but that's what's going on. They just decided those are impossible to throw strikes. We're just gonna go up to and wait for a walk, and that's what they did. And so he walked like the first three batters, and so bases are full. Nobody's gotten a hit. Bases are loaded, but nobody's out. So even if you get any wood on the ball whatsoever, you're probably going to score a run. All right, and they eventually the team won rather handily doing that. All right, but if the knuckleballer's finding the strike zone, which is unusual, that all bets are off on that. So enjoy that while you're watching that. So let's go back to the slides here. Okay, so you got this drag formula. So you got the now our drag formula is going to be a little bit different, but you're going to have to find the coefficient of lift. Same thing as the coefficient of drag, but you're going to find the coefficient of lift for your boomerang. And I'll walk you through that in the actual lab portion next week. Okay, in that uh, part. So if a bicyclist doubles his speed, how much more force must be he applied to overcome the air resistance or drag? So if you want to double your speed, look at this. Since v is squared, that means it'll be 4 times. All right, doubles the speed. How much more is the force? So the faster you go, the more drag that you're creating. This is why. You might think, well, what's the difference between 55 miles an hour and 70 miles an hour? Right? Back in some of you, I know there's a handful of you out there that remember the days of driving 55. Johnny Cash even had the commercials. Drive 55. You'll still get there, and you'll save the country. On fuel. This is during the first fuel crisis of the mid 70s. They changed all the speed limits to like 55 to 60. All right, and in Montana, this is ridiculous. But anyway, and because the drag force goes up exponentially with speed. So if you drive just a little bit slower, the amount of energy that's required is way reduced, and the amount of drag is way reduced, and so it's much more fuel efficient, just in 10 miles per hour. All right. Okay. And then power to overcome drag. So there's different mountain bikes. I've met the kind of, and you can do drafting on a train. Rode his bicycle. So the train broke the air resistance for him, so he's able to ride 60 miles an hour. Okay. Skydiving. When a skydiver jumps from a plane, he's in free fall within. I was going to have a skydiving thing where we dropped little monkey, parachute monkeys from, but I didn't have a way to get them to you. So, and besides, this is our last lab that we're doing anyway. And so, as his speed builds up, it increases until the same magnitude as the force of gravity. All right. So the drag increases until it equals gravity, and at that point, the forces are balanced, and the velocity is the same. And so the velocity does not increase anymore because gravity is an accelerant. Okay, so you have these two things equal to each other, and so the terminal velocity of a human being is 2 mg times the density of air, which is what rho is, times the coefficient of drag times the area, the surface area. So if you make the surface area small, see if the surface area hitting it is just your head, then it's 200 miles an hour. Arms outstretched, 120 miles an hour. Why? Because the area is bigger. World record, 614 miles per hour. I think, now what I want you to do is I want you to watch the next video. Joe Kittinger set the world record for the highest jump. Not anymore. Not anymore. And that's in that Stratos. I know it's 8 minutes long, but it's fascinating. And they use the GoPro cameras. And I'd love to show it to you and do commentary over it, but I'm just going to let Art flow over you, and you can watch that on your own. Okay, so that's the next. That's the next video. That's track 8 here, and I'm going to go ahead and log off now, and so you can watch the Stratus. So you can watch how he gains. See, this isn't just about the lab. I'm trying to teach us a little bits and pieces of science here too as we're going along. So he way exceeds it because he's a little bit higher than this, not much. So he goes a little bit fast because he's outside of the atmosphere. Remember, the atmosphere is only about 16 kilometers up or 20 kilometers up above the atmosphere. Okay, no air up there, no air resistance. Then all of a sudden, then he starts hitting the air resistance. You'll see he goes into a pretty violent spin. And if Felix Baumgartner wasn't such a good skydiver, such a professional, and in fact, I think that's Felix here, skydiver, he may not have been able to pull out of that. Okay, so now that we've gone through air pressure, now that we've gone through frictional drag forces, now we're ready to spin. Okay, that'll be the next thing we do is we're ready to spin and then look at your actual homework. All right, or look at your pre-lab. All right, so out here on this one.